Right now, in every neuron in your brain, a tiny electrical spike races down an axon in about a millisecond. This is the action potential, the nervous system's basic signal. Today, follow one from rest to fire and back again. At rest, the inside of a neuron sits at about -70 millivolts, negative compared to the outside. The membrane is far more permeable to potassium than to sodium, so potassium leak channels let it drift outward, setting most of the resting voltage. The sodium-potassium pump keeps working in the background, moving 3 sodium ions out for every 2 potassium ions in, maintaining the gradients, not generating the resting voltage directly. A stimulus depolarizes the membrane, and some depolarization drives voltage toward threshold, around -55 millivolts. There, voltage-gated sodium channels snap open, sodium rushes in, and that charge depolarizes the membrane further, opening still more sodium channels, positive feedback that runs away on its own. That's why the action potential is all or none. A stronger stimulus never makes a bigger spike, only an earlier one. Sodium keeps flooding in until the membrane peaks near +30 millivolts, close to but never quite reaching the sodium equilibrium potential. Just after the peak, the sodium channels and activation gate swings shut, cutting off sodium current. At the same time, the slower voltage-gated potassium channels finally finish opening. Potassium now rushes out, and that outward flow of positive charge repolarizes the membrane, driving it back down toward rest. Those potassium channels close slowly, so potassium keeps leaving after the membrane passes back through rest, dipping toward the potassium equilibrium potential, around -80 to -90 millivolts, the after-hyperpolarization or undershoot. As the channels finally close and reset to their resting state, the membrane settles back to -70, while the sodium-potassium pump keeps restoring the ions that crossed, ready for the next spike. Right after a spike, the sodium channels and activation gates stay shut, so nothing can fire a second spike, the absolute refractory period, which caps how fast a neuron can fire. As those gates reopen, a relative refractory period follows, needing a stronger stimulus. Together, these force the signal to travel one way down the axon, never backward. The sequence: rest, threshold, overshoot, repolarization, undershoot, reset, one traveling, one-way signal.